look at the logarithmic function. Now, just as we call the most important exponential graph the one that has y equals e to the power of x, we call it the exponential function to distinguish how important it is from other ones. We also call the logarithmic function the logarithmic function that has the base of e, and it's similarly important. Now, we've already seen that logarithmic functions and exponential functions are reflections of each other around the line y equals x. So if we know how to draw one, we know how to draw the other. Now, if our original exponential function has an asymptote along the x-axis, then our logarithmic function has an asymptote on the y-axis. And just as our exponential function goes through 1 on the y-axis, our logarithmic function goes through 1 on the x-axis. Another thing we already know about is the gradient of our exponential function at this point. It's 1, and so the gradient of this one will also be 1. I haven't drawn that, probably quite steep enough. It needs to go up a little bit more sharply, but we get the idea. So we have a gradient of 1, so we should write some notes down of things that we know about. Our logarithmic function has a gradient of 1 at its x-intercept. It also has an intercept at 1, 0. And the other important feature, of course, is the asymptote, which is on the y-axis. We should also note down that it is a reflection of y equals e to the power of x around the line y equals x. Now, this makes a lot of sense. If you reflect something around the line y equals x, you're virtually just swapping the y value and the x value. Algebraically, let's have a look at why this works. If we take our exponential function and we actually just swap places with these two, then we'd have x equals e to the power of y. If we rearrange this and write it as a log, then we can see that it can be written e to the power of y is equal to x. So here we have our logarithmic function, which is the same as this. It's just written in a different format. And we can see that these are reflections around y equals x because they've literally just swapped places with the x and the y. A few other features that we should probably note about this graph, as we did when we looked at the exponential function. If we look at its domain, the values of x that are possible, we can see that this red one here, it only goes from x equals 0 up. But x can't actually equal 0 because we have an asymptote here. So the domain is that x has to be greater than 0. The range, all real y. The shape, it's always concave down as opposed to our exponential curve, which is concave up. And if you look at the behaviour of y and the gradient as x changes, as x approaches infinity, coming along this way, it seems to be flattening out, but technically y also approaches infinity. And the gradient's getting flatter and flatter, isn't it? So it's actually approaching 0. On the other hand, as x approaches 0, it will never actually get there, but as it approaches it, y will approach negative infinity. It's going down this way. And the gradient's getting steeper and steeper, isn't it? So the gradient is actually approaching infinity. Now, a quick look at the notation for the logarithmic function. When we have a log with base e, people often just write it as the log of x. And if you actually don't see what the base is, it's fair to assume that it will be e, because this is the most important logarithmic function that there is. So mathematicians often leave that e out and just write the log of whatever number they're using. We can also write it as ln, and that stands for Neperian or for natural logs. Now, we need to be careful. The ln is okay because it's very clear when you see ln that it's going to be a natural log. And in fact, the natural logs on our calculator, we use the ln button. But be careful with this one. This one could actually mean that it has a base of e, but it's not written. And when you use your calculator, you need to be careful not to just press the log button automatically, because on our calculator, the log button means log with a base of 10. We've seen this before, but it's not a bad time now to just recall that logs and exponentials are inverse functions. And we can take actually any number, x, and we can write it as an exponential or as a log. So if you're writing as an exponential, give it a base of e, and as long as you then write the power as a log also with base e, and then throw in whatever your number was, you'll have the exact same expression but just written as an exponential. You can also write it as a log by writing log, giving it a base of e, and then making it e to the power of something. So basically taking e to the power of something and taking the log of something with base e are opposites. So if you apply both actions to a number, you'll just have that number itself.